All right, the room is full, so we're going to go get started. Today, our colloquium is by Tom Berger. Tom Berger is a familiar face and well known, I think, to everybody here, but because it is our custom, I'm going to introduce him anyhow. Tom received his PhD in astrophysics at Stanford, and afterwards he was a research scientist at the Lockheed Martin Solar and Astrophysics Lab for 15 years until 2012, when he moved to become the project scientist for the DKI Solar Telescope, and he moved to Sunspot, New Mexico. He was there for about 2 years, and then he moved to Boulder to become the second director of the Space Weather Prediction Center, NOAA Space Weather Prediction Center. He is currently transitioning to the University of Colorado, where he will be the founding director of the new Space Weather Technology Research and Education Center, as you can see from his current affiliation. So without further ado, Tom, please go ahead.
Thank you, Alfred. I'm pleased to be here today representing University of Colorado. This is a new initiative. It's a chancellor's grant for 3 years to start a new center at CU, specifically for studying space weather in an applied research and technology development and also education capacity. I wish I had more time today. I might show some slides, but if you have any questions about it, I'll stick around afterwards and certainly be happy to answer any questions. But today's talk will basically be focusing on some research I started about 1.5 years ago with the co-authors you see there, with Alexei Petsov, Valentin, who's here today, Gordon Petrie, who's also here today, Luca Vertella, Nick Argy, Carl Henney, and Kathleen Shirkin, who were at AFRL at the time. And we all had this question of whether or not it would be possible to blend magnetograms successfully from, say, an L5 satellite with something from an L1 location or the Earth in particular. This came up at the L5 meeting because of discussing what would go on an L5 payload. Magnetogram is currently being talked about for the L5 payload. However, there was a lot of talk there that you didn't need to put anything out to L1 or anywhere else in space because we had ground-based magnetograms and you could just meld them together magically and it would work. So some of us thought, we've had some experience with magnetograms which is contrary to that rosy picture. Let's do some research and see if it really can be done as easily as some might hope. And that was the genesis of this work. To back up a little bit and provide some motivation, this is, of course, the Aurora Borealis. Some of you might recognize it. It's something we would like. In this case, it was, I believe, a G2 storm. This is in Tromsø, Norway. And this is, of course, the solar wind and the interactions of the solar wind interacting with the Earth's magnetic field, generating this very visible, the only really visible aspect of space weather. And of course, we'd like to get much better at being able to predict when these storms are going to come down to perhaps the hour, because one of the things we now know, as the saying goes in Alaska, when the aurora is strong, GPS is wrong. So you can guarantee that people here in Tromsø, Norway, are not getting good GPS signal or lock and cannot use that service right now, which is becoming more and more a part of our society. So that's sort of the motivation. We need to be able to predict these storms better, both in timing, arrival, and magnitude. And how do we do that? Well, that comes down to really solar wind forecasting, because that's the driver. That's what's interacting with the magnetic field to produce this geomagnetic storming, which has a lot of effects beyond GPS even. So really what we're looking at is trying to say that fast solar wind streams and interactions, which drive these G1 to sort of G3 level storms, are what we need to predict better. And of course, the solar wind also can influence the arrival time of CMEs, the biggest ones of which can drive the G4 to G5 type storms. So we really need to get better at predicting the overall heliospheric solar wind conditions. As you know, the fast solar wind emanates primarily from coronal holes that correlate with open coronal magnetic field regions on the sun. And so field lines that generally reach directly from the photosphere into interplanetary space are what we're trying to predict using models based on measurements of the solar magnetic field. So item 3 here, current solar wind forecast models calculate, for instance, things like flux tube expansion ratios or distance from coronal hole boundaries using photospheric magnetic field measurements as the boundary conditions to these models. And it turns out that as we've known both empirically and from the models, structure all over the sun can influence the solar wind all over the sun. So that, for instance, we're interested, as I said, mostly in predicting the solar wind conditions at Earth. But it turns out that active region emergence on the backside of the sun can actually influence solar wind flow at the Earth. Similarly, coronal hole shapes are very sensitive to the overall global field structure of the sun. So we really need to know the global magnetic field of the sun in order to do a better job at predicting solar wind and hence geomagnetic storming. And then the last point here is just that the failed solar wind-related geomagnetic storm forecasts are frequently, not always, but pretty much almost always, due to errors in the photospheric magnetic flux boundary conditions that feed these models of the solar wind in the heliosphere. So the high-speed streams coming from coronal holes or the co-rotating interactive regions which occur out in interplanetary space before the solar wind gets to the Earth, these are things that can result in, for instance, the surprise G3 storm of 25 October 2016, and I'll show a little bit about that later in the talk. These are the things we're trying to understand how to predict better given the photospheric magnetic field. And just as a reminder, this is what a coronal hole, a very large one, looks like. In particular, this one has what you might say is a dangerous equatorial extent, because as we know, the Earth is essentially orbiting in the equatorial plane of the sun, plus or minus 7 degrees. And when you see a coronal hole like that stretching down across the equatorial regions, you know that there could be high-speed streams coming out into the Earth. But it's not necessary to have an equatorial coronal hole to have high-speed streams at Earth. Polar coronal holes can cause them as well. So we're really trying to predict, based on, again, the photospheric magnetic field, what the coronal magnetic field is in its configuration, in particular coronal holes. And there's a whole other field here on actually measuring the coronal magnetic field. I won't get into that today. That's really cutting edge. Whoops, what happened there? There was a problem and it closed. Okay, well, that's obvious. Let's try that again. All right. I'll go down. There's the coronal hole. And so we can formulate this as a problem statement. Can we determine the global magnetic field of the sun given only one vantage point in space, namely the one we have right now from Earth or L1 or something in the sun-Earth line? The short answer is no, we can't. But being scientists, we're clever, we extrapolate, we interpolate, we approximate, and we end up with the infamous synoptic magnetogram that many of us have come to both love and hate. This is, and many people are sort of fooled by this picture. What you're seeing here is a latitude-longitude plot of the solar magnetic field, as if the sun were a sphere, and we just unwrapped it, and voila, there's your magnetic field, right? Wrong. The sun never actually looks like that. A synoptic magnetic field is created in various ways, but the classic way is to take the magnetograms that we get from Earth. You see the disk of the sun, you measure the magnetic field, in this case, the longitudinal magnetic field in the photosphere, and you take a stripe right down the middle where you have the highest signal to noise, you know the field is relatively radial, and you just stack those strips together over time to create your synoptic magnetogram. So you can see there that time is going from right to left along the top, and on the bottom we have longitude of the sun, and then latitude along the y-axis. And this is scaled to plus or minus 50 Gauss, so we're really crunching down and saturating the active regions, but it brings out the small scale field well to show it like that. And you can see that as you get more data on different dates, you just stack them together, and then things that go, as time rolls on, things just sort of fall off the right-hand edge and will rotate back around because we have no data on the backside. So the stuff that shows up on the left edge of that map before we have measurements is actually about 14 to 15 days old. So that's the classic method of creating a synoptic map. That's what you're seeing when you see one of those maps. This is the more sophisticated way that the GONG and the SOLAS pipelines use, in which they take essentially the entire disk of the sun minus maybe the 60-degree slice on the eastern edge there, and they use that those entire data from that disk with a cosine to the fourth weighting function of longitude and sort of stack those up over time. So they're actually averaging in new data as it becomes available. Again, it rolls off to the right, and you have to wait for new data to come in on the left as you go across the map. So this takes into account more data, and it's sort of a more robust algorithm for creating a synoptic map. And I'll talk a little bit about that more later. Now, the problem comes in that magnetograms that we're talking about are often, as I mentioned, longitudinal. Sometimes, like with HMI, you can have vector magnetograms, so they're measuring the transverse field. But for the most part, they're using the longitudinal magnetic field, magnetic flux density to be precise, the data that go into these maps, for the data that goes into these maps. And as you can see, basically outside of active regions, as I mentioned, most of the solar field is radial. So what happens when you go to the limb or to the poles, you're suddenly looking at a field that's almost perpendicular to your line of sight, and you're trying to measure the line of sight component of that. So the signal to noise gets very high at the limbs and the poles. And so in practicality, what it comes down to is within about 60 degrees of the disk center, you're okay. Outside of that, your data rapidly becomes very noisy. And as I showed in the Gong Solus pipeline data, for instance, they don't use that 60-degree stripe for that reason, one of the reasons. And what happens is, for instance, you can see here, there's an active region coming around the limb that's been missed by this. It's outside of the 60-degree safe zone, and so a synoptic map made from data on this day will not contain that active region until it rotates further into the safe zone and it then becomes incorporated. But that can have serious ramifications for your solar wind prediction on this particular date, as I'll show. So some people say, well, L5 to the rescue, right? Let's just send a spacecraft out 60 degrees, orbited around the L5 Lagrangian point, and you've got a much larger field of view of the sun. Sometimes erroneously thinking that you can get 2/3 of the globe by doing so. But in reality, as I showed, because of these signal to noise limitations and that 60-degree disk you can picture, the overlap is 60 degrees, but they really only extend 60 degrees on either side. And so in practicality, with an Earth-based and an L5-based magnetograph, yes, you do much better. You capture 60 degrees of extra data, but you only get about half the sun. So you're still missing half the sun, even with those two satellites. Turns out that if you have another satellite out at the L4 point, you get about 240 degrees of total coverage, not 360. So you really need, in order to get 360-degree measurements from these L5 missions, L5, L4, and L3, the balance point that sits behind the sun and is somewhat difficult to access and communicate with. And the other thing to mention here is that you're in the ecliptic still, so you're still not getting the poles very well. You do have advantages of being at L5. You see things rotating. You see things that are going to be in the Sun-Earth line in about 4.5 days. So you've got about 4.5 days of lead time to see new active regions. You've also got a different view of the poles because of the inclination of the orbit of the Earth. And so L5 and L4 do have advantages, but as I'm trying to show here, it's not the panacea that some people might think it is to just put something out there. And in particular, there's been studies, this was by Alexei back in 2016, which show what if you had in the top frame an L5 satellite with its field of view shown in the white box. Let's see if I can use the mouse here. Yeah, so there's the white box of the L5 view. Notice this active region that the L5 view sees. Below, he shows a simulated L1 field of view in which he's taken out that active region from this synoptic map to just say, okay, yes, your synoptic map given just L1 wouldn't have that active region. So let's take it out and let's run a heliospheric current sheet calculation and coronal hole calculation, essentially an open magnetic field model, and see what we get. And what you get are shown on the top and the bottom on the right there. On the top, you can see, including that active region, you get an additional coronal hole extent circled in the blue dashed region there. You also get a much different current sheet in that region. And in particular, you can see the current sheet is dipping down into the ecliptic. So you would actually see a sector change at Earth due to this particular model run. Whereas the bottom, when you just have the L1 and you've missed that active region, you don't see the sector change and you don't see the coronal hole extent properly in your model. So this might not be a drastic misforecast, but you wouldn't be able to forecast solar wind quite accurately given this. So adding L5 or L4, L3, whatever you want data, the do problem statement becomes, can we merge magnetic data from these different viewpoints successfully to get a better map? And the short answer is maybe. It's kind of the point of this talk and also talks that Gordon and others have been giving. And it comes down to, can we intercalibrate different magnetograms? It turns out that's extremely difficult, as I'll show in the rest of the talk. But being scientists, again, we extrapolate, interpolate, approximate, and we try really hard to fit things to a linear fit to say, if we have signal A in magnetogram A, we know that's signal B in magnetogram B. So here is where we get into the meat of the talk. Back in 2003, I did a ground-based and space-based comparison between MDI and what was then called the Advanced Stokes Polarimeter at Sac Peak, and found some really, I was thinking I was going to find a nice linear relationship that would just allow us to calibrate our ground-based data off ASP and MDI off ASP. And what I found was really pretty messy. I redid it again here with HMI and Gong. And this is just a quick and dirty full disk study using the Fitts header data to align the disks and then scale to the pixel size. So what I did was scale MDI to the common pixel size of GONG, somewhat larger pixels, and then plot pixel by pixel across the entire disk to see what we got in the time-honored way of comparing pixels. And this is what you end up with. It's pretty messy. It's somewhat linear. There are correlations there that you can find. However, one of the things that I found in the 2003 study of ground-based of the ASP and MDI data, and also showing up here, is that the polarities are different in terms of their linear slope fits. So you see on the right-hand side, that's the positive polarity. You get a very different slope than you do for the negative polarity branch. And if you try to fit this with just one line, you get a completely different slope. That's the blue line shown there. So this is sort of what happens in almost every study I've seen. You'll get this polarity, asymmetry, and no real one fit given all the polarities on the disk. This is actually going back to that 2003 study. So on the right, you see the ASP flux density map, and on the left, you see MDI, full disk data. We didn't have high-res data for this particular active region I studied. But again, scaling the pixels together and plotting, you see the same thing on the lower plot there. Polarity asymmetry, which is significant. Also saturation, you see it becomes very nonlinear at the higher field strengths in that negative polarity. Even if you don't include the sunspots, so what you're seeing, the fits for the lines don't include the sunspots. Those are the data that are really becoming nonlinear. So anytime you have active regions, you're going to have very nonlinear calibrations. Another study, it was done by Anna Pietrella et al. In 2013 using SOLAS VSM data, comparing it to HMI. They did something a little different. They took a grid of the central tiles that you see on HMI and compared those directly to SOLAS VSM. So the plots below that you're looking at are those individual tiles. And it shows that spatially across the disk, the top row is showing slope, essentially, scaling factor as we would call it in an optimistic linear fit. And the bottom row is showing correlation coefficient, the Pearson correlation coefficient. And what this shows is even across the disk, you have great variation. What you'd like to see is those being pure black on the top row so that you have a slope of 1. You can see also that the weaker fields on the left have different slopes than the stronger fields on the right. And then there are regions near the limb or the poles where there's insufficient data to really get a good fit using this method. So again, big mess. Not surprising though. And finally, we're moving on now to say, well, that's the disk data. What about taking synoptic magnetograms once they've been created by whatever method you've created your synoptic magnetogram? Maybe we can just merge those data, because these are the data that get fed into the potential field source surface models to predict solar wind in the heliosphere. So let's look at just comparing the synoptic magnetograms once they've been created by whatever algorithm you have. So on the top row here, we have an HMI synoptic magnetogram created by taking central strips over days, because they have so much data they can afford to do that. Then you see the GONG magnetogram processed by NSO in the middle. And on the bottom, in order to make this comparison as optimistic as possible, Gordon Petrie took the HMI magnetogram and processed it through the GONG pipeline, scaled it, I believe using a single linear scale. Correct me if I'm wrong, Gordon, but it's a single linear scale and spatially degraded, but processed the way the GONG synoptic maps are made to create the synoptic map on the bottom. So that's what we're going to compare. HMI processed through the GONG pipeline with the GONG synoptic map. And voila, this is looking much better. Now, why is that? This was kind of surprising to me because I'm used to, comparing magnetograms pixel to pixel and finding big messes. This is, again, pixel to pixel for those 360 by 180 pixels they have in a synoptic map. And you get a pretty nice linear fit. The polarity asymmetry is almost non-existent. A single slope fits quite well. So this is promising. However, it is, as I mentioned, a little optimistic because Pete Riley did a much more thorough study back in 2014 where he took 6 different synoptic map creations and tried to cross-calibrate all of them using various different statistical methods. You see the 6 there ranging from Mount Wilson and the Wilcox Solar Observatory as the older ground-based ones through HMI. On the right, what you see is for each observatory, all those lines are the other observatories' correlation coefficients. So how well do these maps statistically correlate with each other? And the dash and the solid represent two different analysis methods. And you can see there's some good news and some really bad news here. There's essentially very little correlation, for instance, between Mount Wilson Observatory and HMI. And this is also plotted by latitude. He took latitude band averages. So for any latitude on the sun, HMI and Mount Wilson have very low correlation coefficients. But there are some better correlations between, for instance, SOLAS and HMI. It's a little better, but it's not. You'd like everything to be a straight line at the top of a correlation coefficient of 1, and that's the ideal condition in which every pixel is perfectly correlated by a linear scaling coefficient with the other pixel, the equivalent pixel on the other map. But as you can see here, this is again illustrating the complexities when you don't have, for instance, these are not processed with the same pipelines. These are processed as they're processed, and then they're scaled to a common plate scale, but it's not the same process, which is maybe a little bit more realistic for how you would end up having to work with differing instruments. So the news isn't as rosy as you might think, given that one example that I showed where we did get a very well worked and very hard, we worked hard to get a very good linear correlation there. So one of the things we wanted to do is say, well, let's now go ahead and try to simulate what an Earth-based and L5 map would give you, and is there any difference in that? In other words, let's do the best we can with simulating something out at L5 and at Earth, and put those together in a single synoptic map and see if we see any differences. So Gordon constructed an artificial blended map, if you will. And what he did is he took essentially the GONG processing pipeline, which has this cosine to the fourth latitude dependence, and he used one from GONG, and he used HMI data in another cosine to the fourth latitude dependence shifted by 60 degrees. So this is these two instruments just marching along the synoptic map 60 degrees apart, creating this blended map, which you see on the bottom. Now, by eye, it doesn't look much different at all from the GONG or the HMI GONG processed maps. And maybe that's not surprising, given it's the same pipeline, the same two we looked at before, but it is created a little differently. It's got these two now marching along to give you a blended map. And this is the pixel by pixel correlation. You can see here that, again, it's really good. And I think, again, we're just showing that when you process something through the same synoptic pipeline, you have a linear scaling factor you use, and then you degrade it down to 1 degree resolution, you get a pretty good correlation coefficient. So this is promising, but again, it's not really a true simulation. It's the best we can do now because there isn't anything in space at L5 to give us that off-angle look. But we went ahead and we said, okay, let's take these now and feed them into WSA in little simulations of the solar wind and see what we get out. So on the left here, you see a GONG magnetogram feeding into the WSA model, creating a current sheet in the middle. And then on the bottom, you see the coronal hole map, which is the coronal holes are in color. On the background is the other flux map. And then the dark lines are the equatorial connections of the coronal holes. On the right is the HMI magnetogram processed through the NSO pipeline, and here some differences start to show up. Based on the small scale differences in those synoptic magnetogram maps, you can start to see differences in how the model interprets those in terms of solar wind. In particular, on the bottom, you can see that the coronal hole structure is quite different. There seems to be a stronger response at the poles, perhaps because there's slightly lower signal or higher signal to noise in HMI data there. It's not clear, but there's clear differences coming out in these two. Now, if you process this into the sector boundary changes and the actual wind speed at 1 AU, you can see that in both cases, essentially what's happened is, in the case of HMI, you've got a false alarm of a very high-speed stream. It's not clear where the model came up with that, but it didn't exist. I should say that the black data here are the actual solar wind data from ACE, and the blue is the prediction of the model. So you can see there a false alarm from the model predicting a high-speed stream that didn't exist. The sector boundary changes on the top row are pretty good. That's not too hard to get right, but the wind speed is hard to get right. And for some reason, GONG did not have this large overprediction, even though these are the exact same synoptic maps processed through the GONG pipeline. In other words, the same Carrington rotation processed through the GONG pipeline. You get very different results from HMI and GONG here. And the other thing to notice is that both of them did very poorly on this high-speed stream in late October, October 18th, I believe. They missed it completely, and that was missed in the forecast as well at SWPC. So SWPC did not have anything out for a G1 or a G2 on that date. This, I think, got up to a G2. Yeah?
Sorry to interrupt. A quick question. Is it WSA prediction propagated to 1AU or is it WSA propagated?
It's WSA propagated to 1AU, thank you. It's the 1D kinematic propagation.
Okay.
But I don't think Enlil caught this high-speed stream either.
Is there a CME at that time?
No. No. So, as I'll show later, you can catch this high-speed stream with proper polar processing, or augmentation, you might call it. So now let's take a look at GONG, again on the right, same thing as I showed last time, versus the blended HMI versus GONG, and here you see some more differences. Perhaps because you have the higher signal-to-noise propagating in the map differently, you do get, again, slightly different coronal hole boundaries, more connection to the equator, particularly in the later part of October, which is on the left-hand side of these maps, but not too huge in terms of the differences. So again, if you propagate using the 1D kinematic code from the WSA solution out to 1AU, you're still missing the high-speed stream, even though you've blended in the HMI data on the earlier times. So that's the result of that. Now, can we do better in catching this high-speed stream? Because that's ultimately, again, the goal of this work, is motivating better forecasts of high-speed streams and therefore better geomagnetic storm forecasts. And the answer is, if you use yet another model, yes. And that other model is called ADAPT. It's the Air Force Data Assimilative Photospheric Transport Model, I think, which is essentially taking and there are several of these flux transport models out there. The Lockheed Model is one that's used quite often as well, where you take the magnetic field data and artificially transport it using known meridional flows, known differential rotation, and you get the backside structure this way. So you're essentially simulating what you think the sun would be doing with this magnetic field on the backside of the sun, even though you can't see it. Now you don't see active region emergences, of course, through this. It's not emerging active regions. It's just saying, given what I see on the front, I'm going to propagate it around the back with these flows that we know about. And you tend to get, because you have meridional flows that are fairly well parameterized, you tend to get better polar field data than you would from the straight magnetogram. So that's shown here in that you can see on the right, the ADAPT model plus GONG data gives you a stronger southern pole field structure than you get in the raw data itself. And it turns out that's the main significance of this, because when you then run it through the 1D kinematic model, as I'm showing on the lower center there, bingo, you catch that high-speed stream. And it's kind of hard to see why, because if you look at the current sheet maps, for instance, they look identical, but if you look at the coronal hole map in detail, you can see that where I've circled it in red there in the late October high-speed stream, you do have more equatorial connections. The hole's a little bigger, and maybe that's all it took to push this one over into the G2 territory. So, yeah. It's late October, so we're looking almost polar at the north, as good as we can at the North Pole. So I think it's pretty low.
You think it's pretty even?
Yeah. So that was one of the good news things out of this study, is that yes, the ADAPT model, even though of course it's not giving us what we want, which is the real total field of the sun, it really is helping you predict the polar fields better, and the polar fields really do apparently have a strong influence on what you see in at least high-speed streams from coronal holes. So good piece of news there. So I'm just going to wrap up real quickly. We'll have plenty of time for discussions. What we found is we confirmed the earlier results, that some of which I showed in the talk, which is namely that determining scaling factors between magnetograms with different sources, different spatial resolutions, different disk positions is challenging. And to find something that works for all of these things is really not possible. This was the concluding sentence, and I quote it all the time from Anna's paper in 2013, because it really hits the nail on the head. You can find linear scaling factors for some conditions at some times between some instruments, but there's no general way to do this. Another conclusion we have here is that with the current state-of-the-art in synoptic magnetogram creation, when using maps processed post facto with the same algorithm and with some instruments, scaling factors can become nearly linear at the spatial resolution of those synoptic maps. And the corollary here is that it really shows that spatial resolution is the key driver to calibrating magnetogram maps. As soon as you go down to the actual native resolutions of these things, the correlations and the linear slopes disappear. But when you smear everything to 1 degree or 3 million kilometers per pixel, suddenly things look kind of nice. The question then becomes, are we ever going to need higher spatial resolution synoptic maps to drive higher fidelity models? If so, then you might be in trouble. You will be in trouble. There's no doubt that as soon as you start to get to higher spatial resolutions, these linear correlations are going to go away, synoptic or full disk or partial disk. So that's really the question for the modelers looking forward. And so far, and I've asked this question, and so far the answer has been maybe. We're not, they're concentrating on the models they have now, and they all use either GONG or SOLAS, or some use HMI as the base inputs, and they're working mostly on getting the physics right in their models. They're not so concerned right now with spatial resolution on the boundary conditions. But given the history of this science, I would guess that 10 years from now we may be really pushing on higher spatial resolution synoptic maps to get better forecasts. So I'll just leave that as the question. And then the largest sources of errors in solar wind forecasting models are the magnetic field boundary conditions to date. The physics of the solar wind propagation through the heliosphere is pretty good. There are interactions in the heliosphere that are tricky to get right, but for the most part, when you talk to the modelers, their biggest pain is from bad magnetogram data, inaccurate magnetogram data, which results in inaccurate forecasts at 1 AU. And so in this, what we've also shown, though, is that better polar fields really help. And so the adapt flux transport model and other models like that really do help capture better polar coronal hole structure and even sometimes equatorial connections. And so it looks like for the time being, using adapt is going to be a good strategy for continuing to improve forecasting. This is just to sort of put a bottom line period on the study, that when you see a synoptic map, generally they are fiction. It's not really the entire sphere of the sun. It's a representation. It's typically the best we can do. The corollary here is that the only way you can really make a synoptic map with current technologies to have at least 2 magnetograms off the sun-Earth line, and preferably out of the ecliptic, as I'll mention soon. But for Lagrangian point missions, you would need L4, L5, and L3 to gain an entire spherical view of the sun using current magnetogram technology. And that technology is also pretty mature. It's not likely that there's going to be some magic technological solution that suddenly allows us to measure transverse fields down to the noise levels we need to get to improve the magnetogram measurements. So I think that statement's going to stand. If you're really set on Lagrangian missions, then you're going to need 3 of them to do the entire sun. Which brings me to my point, which is that the best way to do this, or perhaps the only way to do this, really, is to have a series of drifters in the ecliptic, which give you not only the Lagrangian point views, but a continuously changing viewpoint around the sun, and also, at the same time, out of the ecliptic constellations with identical magnetograph instrumentation on board. So that's a key thing, because then you at least know that you've got the same spectral lines, spatial resolution, temporal resolution. These sorts of things now become, they're taken out of the variable set, and you have a better chance at intercalibration. And so, the ecliptic drifters, that I've called this stereo plus. I really wish we would be looking at that kind of a mission rather than the Lagrangian point missions. I think going to L5 and L4 are both interesting places to be, but it's expensive to park a satellite. It's also typically, when you say you're going to stick something out at a permanent location, people want to make that a very large and capable satellite, so very quickly it becomes a very expensive mission. Whereas you can imagine these drifters being smaller satellites with very dedicated instrumentation, perhaps different instrumentation on different drifters, but identical satellites launched in a co-launch manner that would give you stereo-like coverage, but with more instrumentation, particularly the magnetograph, which unfortunately wasn't on stereo. Yeah.
One of the stereos died. I can't remember which was before or after.
B died on the way around, I think.
But does the one still active have a magnetograph on it?
No, it's
And is it it's not at one of the L points, is it? It's moving,
no.
so
It's coming back to L5, I think. It's going to be at L5 in a couple of years. So, but for what that's worth.
what
Yeah.
does it have on?
It has a coronagraph, a heliospheric imager, and some in situ measurement, magnetic field, particles, things like that. So oh yeah.
UV? Yep.
So it is very useful for the coronagraph, off-angle coronagraph, triangulation of CMEs. And in fact, when stereo they were at L4, L5, and you had SOHO, LASCO at L1, you had the best of all worlds with a really nice three-point view of CMEs coming out. And in fact, that's when SWPSI CME forecasts were the best. The time error on arrival was the lowest, and it was down to plus or minus about 6 hours, whereas now it's 12 to 20 hours typically, which is not good given that your CMEs arrive in sometimes 20 hours, or even, in the fastest case, 14. So yeah, in my opinion, drifters, properly instrumented drifters would be the way to go. Getting out of the ecliptic is, I've been told, expensive and difficult, but I really think if you're going to look at the poles, this is the only way you're really going to do it. And the quintessential example there, which I always like to show, is that here is Jupiter's pole as taken by Cassini in 2000. It wasn't going below Jupiter, it was off at an angle, but it was at an angle where it could see the pole. I don't know the angle exactly, but by extrapolating their orbital paths, voila, they got this polar view of Jupiter. And it's like, oh my God, that's a great shot. And everybody's like, oh, there's the pole of Jupiter. Doesn't look like much is going on. That's kind of interesting. Fast forward to 2017, and you have Juno. And that's what the pole of Jupiter actually looks like when you go over the pole and look straight down at it. So, and I know it's too bad Scott's not here because I know he's a very strong advocate of this as well. I really think that going over the pole of the sun, or at least getting up high enough to get a good view of it, would really show us something about the flow fields up there. I don't expect them to just be straight linear meridional flow going to the pole and sinking down at the middle. I expect it to look something like this. And this could show us a lot about how to model the polar fields in future models. So I'll just leave it at that. Here are the references I use. So all of these papers are similar studies done in much more detail and by more proficient people than myself. So I relied a lot on their work in this talk. And then finally, the contributions and acknowledgments from COIs. Thank you.
There's a lot of time for questions. Axel.
You started off by saying that the synoptic magnetograms are not really representations, 360 degrees representations. One of the things that are characteristic on the magnetograms, synoptic ones, is these trailing structures, right?
Let's see if we can get one up here.
One does not really see that in individual views. Do you think that's actually one of the main differences, or are they actually really present, these trailing structures?
What do you mean by trailing structures?
Are the ones that go to
The streamers to the pole.
yes, instruments to the pole.
The leftovers from
Would they look
Yeah.
the same? Would they look the same?
They are real.
I think they're real, yeah. I mean, you're not getting a true representation of the field structured in detail, but
What else did you have in mind was actually then really different between such an optic one and the actual?
yeah, imagine you had these drifters and you could take an instantaneous image of the full sphere. You'd catch active region emergences on the backside. That's the biggest thing. But you'd also see better coronal hole structure as well. You'd get better coronal hole structure because you'd have, well, one of the things I didn't go into detail is if you had these drifters, because of the ecliptic angle, they have different views of the poles at different times. So you would see the poles more accurately throughout the year of the measurement, or the month of the measurement in the case of a synoptic map. So you get higher signal to noise view of the poles using either L4, L5, or drifters, and that improves your polar field somewhat. How big a factor that can be, I don't know. Again, you probably wouldn't ever really get it really right until you went up high enough to get a good signal to noise there.
So it's basically still right. It's just not very accurate. Covering correct.
I don't know what you mean by right. I mean, there was never a time when the sun looked like that, right? Because within a month, all of that stuff has evolved in some way. Maybe not hugely, but in some way. So there's meridional flows, differential rotations, shearing stuff. And in the worst case, there's big active regions that pop up. So never did the sun look like that. Yes?
There is one property that seems very crucial traced by your prominence. If you wrote for that prominences occasionally in high latitude,
Mm-hmm.
then it will be very interesting to find out if it's credible that they actually lie anywhere close to the neutral line, that you have sometimes half a month too late or 1 week too late. Oh yeah.
Yeah, there's a really nice prominence in this movie. You can see it here. So this is a very long filament channel, and that's a very good point, BC, because you can see it parallels the coronal hole edge perfectly. So there is something going on with.
So how well is that comparing methodologically?
I don't know. That's a very good question. I don't know of any studies that have taken synoptic maps and tried to do filament channel extrapolations. It seems like there probably is studies like that out there, but I'm.
Earlier studies could assume that the magnetograms are okay.
Yeah.
And then they will force your filaments to lie over it.
Yeah.
You know how we all get carried away.
Yes, I'm familiar with that. Yeah, Mark.
The study by Anthony Yates with the global magnetosphere code using the locations and timing of active region appearances to drive the global model. It was over, I don't exactly remember how long, but we start without any filament channels. We pop up these active regions, and after 6 weeks, they start to get the locations and the chirality of the filaments correct.
Yeah, I'm familiar with that paper. I was almost going to show a slide from their study too, and I thought I wouldn't have enough time, so I guess I talked fast. But yeah, that study went over, I think, a cycle. It was
so they had an earlier one, and then they extended it.
Yeah. Yeah. So that's another approach that's being taken, and Gordon gave a talk at NSO yesterday, and that mentioned that, and in fact he's doing that. You can actually model using models of solar cycles that have either historically recorded active region emergences and or artificial active region emergences. You can model the sun exactly and then find out what it would look like from various vantage points or with various different instrumentation at different vantage points. And that's a good way to look at it in terms of what you gain by having different vantage points. But I'm more of an observer, so I just want to go and measure the stuff. So.
What would it take to just have a satellite that would orbit the sun perpendicular? The reasons.
A big delta V.
$3 or $4 billion.
That's not much.
Well, if it's big, I don't know. I mean, that's the thing. If we're talking,
Not much money.
there you go. This,
Not from NSA, from DOD.
yeah, get some national security in there, and you've got it. Katie. Yeah.
I guess I'm curious if the big mess, that you were talking about in terms of the correlations and stuff, isn't caused at some level by all the intervening steps. I mean, you're kind of in these comparisons and these mergers. There's kind of a focus of doing things after the fact, right? I mean, they've already gone through all the pipelines. So you've already got different lines and everything like that.
Yeah.
But these kinds of mergers, and when we did some studies way back, you really have to start with polarization signals and normalize those, or at least get those on the same footing, and then process everything with the same algorithms. And then you can start to say, that these are starting to, maybe we can actually merge these at that point. I mean, some of the work we showed that even, how you resample, rebin, merge, smear, whatever, can actually change your results.
Oh yeah, absolutely.
So
That's
I'm just
yeah.
curious if one went back to, let's say, HMI plus solar polarization, now different lines, but similar enough, and started from that. To what extent
I think that's your only hope, and that's kind of the point of that last point. Is if you really want to do this, ideally you could maybe get away with different instruments, but you'd have similar instruments. But even we all know that even similar instruments are very difficult to cross calibrate. I mean, look at Gong, identical instruments, and it took years to get that calibration straight. So
I guess the statements of we cannot do this.
they're now very good.
But the statements of we cannot do this devastating, given that the way that it's been done so far is just to take the end. It's the cake you've already baked, not the tight. You haven't gone back to the mixing the flour together.
That's true. I mean, but the problem is going back to that level with existing data sets. That's a large. It's a large effort. So.
Stating that statement, it seems like that would be an obvious place to start.
Yeah, I don't know, Gordon. Is there an effort to do? Since you mentioned HMI and SOLAS.
Go back to the polarization system.
Yeah, Joe's working on something like that. Yeah. 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 So I mean that's a good point though, is that I think that one of the things that I've come to in looking at this for a while is that spatial resolution is the major driver. And so if your instruments don't have the same spatial resolution, I don't think it matters how far back into the cake batter you go, you're never going to get them to really come together. If they're close, you probably have a shot, but when you're working with ground-based, especially when you have variable spatial resolution with seeing, and you say, oh, we're just going to merge that with a space-based instrument with no seeing, I think that's where I would say you're out of luck, unless you're going to smear everything to 3 million kilometer pixels. Yeah, Valentin had a point, and then I'll get to the back.
Yeah, so there is one drifter that is coming, which is Solar Orbiter.
Mm-hmm.
Solar Orbiter is going to be flying around and having all kinds of line of sight, constantly changing.
Yeah.
And there's a magnetogram on board.
Mm-hmm.
And the plan was always to be able to merge the data from Solar Orbiter with the data from line of sight from the Earth, HMI, GONG, whatever. So we knew the problem, because the problem was known in the past, and what we decided to do there is not to make sure we can calibrate, say, Solar Orbiter with GONG, but calibrate Solar Orbiter with an MHD simulation and calibrate GONG with an MHD simulation. So it's this is the end-to-end that Gordon was saying. You try to put all of the spatial resolution, spectral resolution, everything, but you calibrate to the same thing. You calibrate back to the sun. We're using a Matthias Rampo simulation, and we call this the sun. And that's what we're trying to do. So instead of, I think the problem is always calibrating SOLIS versus HMI or HMI versus...
And existing data, like Katie said,
So,
you've got this,
So you calibrate the instrument with all of the properties, as many as you know, to a known simulation and to the same simulation. And you understand how you go to the simulation, and from there you're going to learn how to intercalibrate. That's what we're trying to do.
Yeah.
And it's going to be important that we succeed in doing that because of Solar Orbiter, that is.
Yeah.
It's going to be the one thing that is, well, I hope soon, going to be flying around and giving us data.
The only caveat I see there is that you've got to have a really good model for seeing for your ground-based instruments, and that's tough because you've got this variable spatial resolution that.
I think you're right, but GONG really has so bad seeing there that it's always bad.
Again, smearing out helps. Yeah, smearing everything helps.
That's what I'm saying.
Yeah. There's a question in the back.
Yeah, when you had the successful correlation between the synoptic maps, and you said you put HMI from the GONG pipeline, does that include the sort of forming the maps using the much of the disk, not just a strip in the middle?
I think so. Gordon created those, and I think that's.
So does the improvement just come down to averaging? Because when you're doing it like that, every pixel's getting averaged like along the time. Is that what makes the improvement?
Well, I mean, not every pixel, because they get the cosine to the fourth latitude drop off. So at a certain point, you're not averaging anymore. You're just letting the old data stay. But I'm sure that.
Yeah, you got to, at least you have an average of the pixel size.
Yeah.
So, here my question is, how much data has been stored that you could do a reanalysis with the 60-degree inclusion? Because it would be very interesting to look at the development of synoptic maps, true synoptic maps, for a very long time. So, you know how far back one could go?
I mean, it depends on what instruments you want to use for that. It's basically how.
Yeah, and you would have
Yeah.
to ask for each instrument
Yeah.
that question.
Well, the Wilcox Solar Observatory started up in '62 or something, so you've got quite a few Carrington rotations there. But chaining those together, I mean, that's kind of what Pete Riley did in his study, as I showed us. He tried to go back and look at some of the oldest existing synoptic maps. Yeah, probably.
But when did their magnetogram?
But again, you run into this. You can see the differences in the magnetogram, in the synoptic maps between these. Creating a uniform data series out of that is where Wilcox is on the top and Mount Wilson is there in the middle. I mean, Mount Wilson, for the most part, seems in spatial resolution, seems somewhat compatible with Gong and Solus. I don't know. Luca would know.
You better.
Yeah, it's all the same error, right? Yeah. So,
I'd like to know, I mean, you basically are talking about the lower boundary condition
mhm.
exclusively. And really what I want to know is, what is it about the coronal, the solar wind, and the magnetism spreading through the sun that makes you believe that something like a solar surface model is meaningful? I mean, I can see there are certain arguments you can use, like the field might be more potential. On the other hand, that boundary condition is in a region where, especially the active region, there is no potential field.
Yeah.
So the rest of the model seems to be unreasonable to expect such a simple model to work. I just find it, I'm not familiar with this because I'm not particularly interested in space weather, but it seems to me that the difference between what's actually going on in solar wind and what's modeled in that outer layers from which you get to the Earth, why is it that this is in any way reasonable?
Well, I guess you can only cite the empirical evidence that these models do a pretty good job when they get the boundary condition right. They can capture pretty accurately this high-speed stream structure, things like that. In terms of, yeah, I guess I'll just leave it at that. There are people in this room who know more about this.
I want to say that.
Sure, yeah.
I think, so I may sound critical, but that's not my intention. I think there's as much anxiety over the validity of simulations model as I do with the data. And I've often felt that you would be given, say, a simulation or theories given very accurate data. I would say the problem is so hard that I don't know what to do with it. You know what I'm saying?
Mm-hmm.
And that's why the transverse field has been measured for so long, and they haven't gotten very far with it. For a very fundamental reason, you measure it within the photosphere. And then all these guys with phosphate field model, they want to live in the chromosphere and Earth. So it's something like that. So when we say we compare models to observations, I'm more optimistic on field. It's a good exercise. So how long can we tolerate for 10 years to carry? And then we remain about the level of excellence we're not impressed with. We're not getting beyond that. Why do I say we're not getting beyond that? Because we couldn't articulate a good physical process or a good physical effect so that every time you present, you say, with simulation versus data, I would say it doesn't work because this problem is in there, but it's not explained well. I think that is what is missing. And then when it works very well with a potential model, I would say I would shrink back too, because then you're doing better than you're supposed to be doing. That's for science is very dangerous. You know what I'm saying?
Yeah,
but
yeah.
For instance,
I know what you're saying.
model is an axisymmetric model, and it could predict so well. Then I say you're in trouble because when I give you a 3D model, then where is the room for improvement?
Yeah, I see your point. I guess I would just answer by saying, putting on my operational hat a little bit and saying, if the forecast is good, and it is good now, but it needs to be better, and we can make it better by getting better data into it, then we're making incremental progress in that way. Is it scientifically perfect? No. Will it ever be? Probably not. But the goal, at least on that in that realm, is to just get that forecast better, so you get some better lead time.
I prefer something like what Valentin was referring to. Once you got this pocket probe going in, and you got in situ measurement, is that coming up as surprises? According to the old man, he said, well, this is a new instrument. It's always full of surprises as soon as you cross the observational frontier. So
Yeah.
I think that probably is useful.
Can I answer? I fully agree, and I think with Parker Solar Pro and Solar Orbiter, we're going to learn a lot, and it's going to be fantastic. So I'm really excited with these missions. But then to your question of why this is working, I will say one thing. Here what is important and why this is working is because the heliospheric fields are dominated by the vertical fields in the coronal holes. The vertical fields in the coronal hole is what really matters of 1 AU. And vertical fields are vertical fields, so they don't have the complexity. So that's basically what this does a relatively good job. We still need to put a lot of physics. We need to do a lot of work and understand the coronal heating and everything. But if this is working, it's because of the
I can resonate with that.
unipolar fields in coronal hole, which are not that complex after all.
Yes, that's a very good way to put it.
Yeah,
I agree.
really can
Yeah.
resonate with that. In other words, you basically are responding to the challenge and put forward. What is simply the complexity in there? Could you identify to say this is one essential thing that I didn't need the refinement, and then if you spend all your time refining something that is not so crucial, then it's good to do it because there may be surprises coming up.
Yeah, I guess, again, this isn't my field, but I've been going to some meetings recently, and I've been interested to learn that, as Valentin points out, the polar fast winds from relatively vertical open fields is a fairly well understood and relatively well modeled problem. The problem they're wrestling with now is the source of the slower solar wind. That's not clear where that's emanating from. Because if it is true that the polar coronal holes and radial fields are dominating the heliospheric flows, how come we see such huge variations in the wind all the way down to 300 kilometers per second? What's happening there? It's not a coronal hole that's causing those winds, but it's beyond my field of expertise. Mark.
As an example of how we can improve the results based on better models, what Tom showed actually is that not better data give us better results, but a better model by having a surface flux transport model transport the flux to the poles gave us an improvement in matching the solar wind. So it was actually the model that did us, not the data.
In this case, yeah, because it turns out those polar fields are critical for getting it right. So.
Last question, Michael.
So put this into a very simple picture. I kind of imagine a sun that doesn't have any flares or coronal mass ejection, just has this sort of slowly varying patterns of magnetic patches with coronal holes where sort of it's vertical, and then every once in a while the Earth kind of looks onto a coronal hole, and that is when sort of we get a geomagnetic storm out of, I mean, you could say the quiet sun, in a way. Now, we know that there is a lot more action, and when there's more action, do we really understand when sort of there is a really big, fast coronal mass ejection, how the heliospheric magnetic field is disturbed along the way? Do we understand that?
No, I don't think so. I don't think they're. For instance, the Enlil model, which right now is predicting coronal mass ejection arrival time, has no magnetic field in it. So it's purely hydrodynamic. So the magnetic interactions in the heliosphere are not even attempted to be modeled at this
There are
point.
models with that program magnetized CMEs, the one in Europe called Euphoria. Starting propagating, but you don't have boundary conditions.
Yeah, right. And so we're getting there, but I would agree that to me is the more interesting prediction. I think it's just interesting that we're still struggling to make the quiet sun solar wind predictions accurately. We're very far from making accurate solar eruption predictions and propagating those solar eruptions. Even if we were able to predict when that active region is going to erupt, then propagating it accurately to 1 AU is even more difficult.
But it could be that you cannot do that because there is no quiet sun. It could be that's sort of a mirage.
Should we leave it at that?
All right, let's thank Tom again.